Okay, we discussed in the previous class that how to eliminate this baseline wonder noise from ECG signal. So we used very basic operator, which was the first order difference, and which resulted in a frequency response like this, 0 to fs by 2. Okay, then we have modified it somehow. We got another response like this. So at a frequency of fs by 2, there is a null point at 0, so the gain drops to 0 again at fs by 2. So somehow the high frequency noise amplification problem was solved. Okay. But what actually we want is a response which, which should remain constant beyond a certain frequency, very small frequency, which is less than generally 1 Hertz, maybe suppose 0.7 Hertz. Okay. So from 0 to 0.7 Hertz, the gain will increase, and beyond 0.7 Hertz, it should remain flat. It should remain constant at 1. Okay. So how you can modify the transfer function? So for the first order difference, you have a transfer function like this. It was 1 by t, 1 minus z inverse. Okay. Which gives you a frequency response like this. Now in order to achieve a frequency response like this, what we do? We simply place one pole close to the 0. If you see the pole 0 plot of this transfer function, sorry, so this is my unit circle, and you have 0 at z is equal to 1. Okay. If I place a pole very close to the unit circle, since see we want to maintain a constant gain after a cutoff frequency or a very low frequency of suppose up to 0.7 or 1 Hertz, so the gain has to be boosted. Okay, so in order to boost this gain, it means along with zeros you have to insert a pole here. So if I insert a pole on this real axis at a point very close to the unit circle, but it must be inside the circle because it is a pole, otherwise it can make the system unstable. So I have a pole at a point on the real axis, suppose very close to the unit circle, that is 0.995 maybe. Okay, and because of this pole, the transfer function will change. Okay, so the transfer function of the system, it now becomes 1 by t 1 minus z inverse upon 1 minus 0.995 z inverse. So you have pole at this point at z is equal to 0.995. Okay, or you can write it as 1 by t z minus 1 upon z minus 0.995. This is my transfer function. Now if you evaluate its frequency response, that is in place of z you replace it with e raised to power j omega and you find the magnitude. So it will be 1 by t e raised to power j omega minus 1 divided by e raised to power j omega minus 0.995. So as the frequency will change, so at this point your omega is 0. So as this phasor will rotate along this unit circle, your frequency will go on increasing. So at this point we get omega is equal to pi by 4. Then at this point we get omega is equal to pi. So this is pi by 2. Then omega is equal to pi and so on. So 0 to 2 pi, or it can be taken from 0 to minus pi also. You can take it as minus pi by 2 or 3 pi by 4. Okay. So if you see to this graph, if you find its magnitude for different values of omega, what you will get? E raised to power j omega minus 1, it is basically a difference factor. So e raised to power j omega, it represents any point on the unit circle. Okay, suppose it may be here, it may be here, depending upon what is the value of omega. So e raised to power j omega minus 1 is what? This factor is e raised to power j omega, and this is 1. So the difference between them, it gives you this distance factor. Okay, so if it goes here, if this is e raised to power j omega, e raised to power j omega minus 1 is this distance. Okay, so e raised to power j omega minus 1 or z minus 1 is basically the distance of a particular point on the unit circle corresponding to a particular frequency from this 0. Okay, so this, as this unit circle moves, as this z or this omega moves, it increases. So the distance between this point and this 0, it goes on increasing. Now since we have placed a pole which is very close to the unit circle, 0.995, so z minus 0.995 or e raised to power j omega minus 0.995 is now the distance between the point on the unit circle and this pole. Okay, so in one case, if the point is here, this is my distance. If the omega goes to here, this is z minus 0.995. If omega goes here, this is z minus 0.995. So since they are divided by each other, okay, and these two distances, they are almost equal because the pole and the 0, they are very close to each other. So as a result, beyond a certain low frequency, this gain will be constant. Okay, so by simply placing a pole near the 0, you can boost this gain and you can have a flat response in the frequency domain. Okay, this is how you can eliminate this baseline wanders. Or more generally in the DSP, when we use filters for removal of low frequency artifacts, so we generally use a FIR filter. You can also design like that. A FIR high pass filter you have to use with a cutoff frequency of 0.7 Hz. So you may design it using a window method. Okay, that we already know. Then let's see, this pole zero placement is a very simple technique to design filters. It is also used to design notch filters. Notch filters are used to eliminate this power line frequency, either it is 50 Hz or 60 Hz. Okay, so in India we have 50 Hz, in some countries it is 60 Hz. So if ECG is mixed with a 60 Hz or 50 Hz power line frequency, so you have to eliminate this from this signal. So what you need is a frequency response like this. So at this frequency of 60 Hz, you should have a 0. Okay, so how you can design this filter? In the Z plane, what it means, this is the unit circle, so this corresponds to the DC frequency z is equal to 1 or f is equal to 0. So so it means corresponding to a frequency of 60 Hz, you have to place 0 on this unit circle. Okay, so if this is the frequency corresponding to 60 Hz, and since it is in a complex, so it must be in conjugate pairs, so I have to place a 0 at minus 60 Hz also. So if you place two zeros on the unit circle corresponding to the frequency of 60 Hz and you get a transfer function from that, that will be simply a notch filter. Okay, because at 60 Hz is 0, it means that frequency is stopped. Okay, now where exactly the 0 will be placed, that depends upon the sampling frequency. So if your power line frequency is 60 Hz and if your sampling frequency is suppose 1000 Hz or 1 kilohertz, what will be the frequency where this 0 will be placed, or what will be the point in the z plane? So you simply get omega is equal to plus minus 2 pi into f naught by fs. This is the point where this frequency corresponds to a frequency of, so 60 Hz frequency is basically mapped to the digital frequency using this. So it becomes around 0.377 radians. So if you convert this into degrees, you will get plus minus 21.6 degree. Okay, so at angle of 21.6 degree you have one zero. Similarly, minus 21.6 degree you have another zero. Now once you have the location of this zero, this is now 1 0 z1, this is another zero, so z2. So you can see what is the z1 and z2. So if you know this, now this distance is 1, this angle is 21.6 degree. So what is this point in z plane? It is simply cos of omega plus, if I take it as omega naught, so it is cos of omega naught plus j sine of omega naught, and this is cos of omega naught minus j sine of omega naught. So omega naught is now given to you 0.377. So if you put this into this, you will get a point in the z plane. Okay, so z1 and z2, in this case it becomes 0.9297 plus minus j 0.3681. Okay, so this is the location of the zeros, z plane. Now once you get the location of zeros, you can find the transfer function h of z. It will be 1 minus z inverse z1 into 1 minus z inverse z2. Okay, so if you put z1 z2 from this, you will get the transfer function. It becomes 1 point minus 1.1.859 z inverse plus z to the power minus 2. So this becomes my notch filter, which will eliminate this 60 Hz frequency from the signal. Okay, so many times not only this frequency of 60 Hz corrupts this biomedical signals, but its harmonics are also present. That means we have a frequency at 120 Hz and at 180 Hz and so on. Okay. So the filter that you design to eliminate the 60 Hz and its harmonics, we call it as a comb filter in place of notch filter, because it takes the shape of a comb. Okay, so you'll have one null point at 60 Hz, another null point at 120 Hz, another null point at 180 Hz, 240 and so on. Okay, so you can design again the same filter using the same technique. So you have to place now zeros corresponding to the frequency of 120 Hz also, 180 Hz, 240 Hz, 300 Hz, how many harmonics you want to eliminate. Okay, so one frequency, two zeros will be here corresponding to this frequency of 60 Hz, 60 and minus 60. Then you have to place two more zeros corresponding to this frequency of 120 Hz. So that may lie anywhere on the circle, suppose it is here. Okay, so this you have to compute, just like we have done in the notch filter. Similarly, for 180 Hz, you have to place two more zeros. And for 240 Hz. Okay, So once you compute all these zeros, z1, z2, z3 and so on. So 1 minus z inverse into z1 multiplied with 1 minus z inverse z2 and so on, you can get the transfer function. Okay, so you can design a comb filter like this. So I will show you one example where it is shown that how this power line frequency is basically removed from the signal using notch filter. Okay, so this is a ECG signal with 60 Hz interference without any harmonics. Okay, and this is the filter, this is the signal that is obtained after processing this signal through a notch filter. Okay, so the cutoff frequency of 60 Hz, the filter that we have just designed. So you can see that this noisy component in the signal, it is removed. You get a clean ECG signal. Okay. So apart from these time domain filters, there are some frequency domain filters that are explicitly, you can say, described in the frequency domain. Okay. So you may take one such case from those, like we have Butterworth filter. Okay.